So, hi everybody. Let us start our seminar today. It's my pleasure to introduce Professor Leandro Vendramin from Vrije Universiteit Brussel. He got PhD in 2010 from Universidad de Buenos Aires. After postdoctoral position in Germany and Edinburgh, he served as professor in Buenos Aires and as a visiting professor at the New York University in Shanghai. In 2021, he moved to Brussels and currently he's working here as professor. The lecture of title of his lecture today is Nichols algebra over groups. Please, Leandro.
Thank you very much. So yes, the plan is to give an overview talk about Nichols algebras and their classification, and also somehow some applications. Why we care about Nichols algebras. So it all starts with solutions to the Yang-Baxter equation. So with braided vector spaces. So what is a braided vector space? Well, you have a vector space over a field K and a bijective linear map from V tensor V into V tensor V, satisfying the braid relation, which is this equation that I wrote there and has that very nice picture that you see. Okay, so the idea is that, well, this is your starting point, and from this you will construct some crazy algebra, which is known as the Nichols algebra of B. So just in case you want to see this concretely, well, suppose that V has dimension n, then you fix a basis from V1 to Vn, and then the tensor product of V tensor V, as you know, is a vector space of dimension n squared, and you can take as a basis Vi tensor Vj running over all I and j's from 1 to n. And the tensor product, in this case, if you just use matrices instead of linear maps, is the Kronecker product of matrices, which is given by this expression that I wrote there. And yeah, here you have, for example, a concrete instance of, or a concrete solution of the braid equation. You can take this R matrix, 1 over square root of 2, and then that matrix that you see there, and you can easily check by hand or using some computer that well, indeed, this is a solution of the braid equation, right? Good. So this is not the kind of example I would like to study. I would like to study other examples. And the first family of braided vector spaces I'm interested in is that of braided vector spaces of diagonal type. This is very, very important because it's deeply connected with Lie theory, with a lot of things in Lie theory, in particular with quantum groups. So the definition is as follows. So you have a vector space V, and then say finite dimensional with a basis, say x1, x2 up to x theta. And then what you do essentially is to flip and maybe put some constants. Okay, this is always a braiding, meaning a solution of the braid equation. And here you can see that you have no constraints over on the constant Qij. As long as they are non-zero, which is something that you need for the invertibility of the map C, then you will always have a braiding. Okay, these are, as I said, these are very important, and they are called braided vector spaces of diagonal type. And then there is a more general family, which is related to groups. Essentially, the idea is that conjugation in groups will give you solutions to the braid equation or the Yang-Baxter equation, and this goes as follows. So suppose that you have a group, and then X is a union of conjugacy classes of G. Then you take V as the vector space with basis in this set X, and then conjugation will give you a braiding. And again, you can twist somehow the conjugation by some non-zero scalar, but now it's a bit different as before, right? So this QXY should satisfy some crazy conditions, just, you know, to guarantee that you will still have a braiding, but it doesn't matter, right? So these are always braiding when these conditions on QXY are satisfied. And this is a very important family of braided vector spaces, and they are called braided vector spaces of group type. And this is more or less what I'm interested in. And then I will explain you why. And the first observation is that, well, if your group G is abelian, then you contain the class of braided vector spaces of diagonal type. Okay, good. Now, what you can do with them? Well, you will produce representations of the braid group. There are several ways of presenting or introducing braid groups. I will take the algebraic one. So the braid group Bn has n-1 generators and the relations that you see there. Essentially, the two generators will commute if they are sufficiently separated. And when they are consecutive, well, they satisfy this sort of braid relation that I put there. Okay. And every time you have a braided vector space, you produce a representation of this group, meaning a group homomorphism from Bn to invertible matrices or invertible maps from V tensor n to V tensor n. And essentially, the only thing what you have to do is to replace your generator sigma I by the braiding in positions I plus 1, which is exactly the formula I wrote there. Okay, and because C is satisfying the braid equation, all the braid relations are the defining relations of the braid group are satisfied, and then you have a group homomorphism. Okay. Now, let me give you a very concrete example of this. So let's put n equals to 4, and well, we will have a picture for the braiding C, which is this way of crossing two strands. And then what is C1 and what is C2? Well, n is equal to 4, which means that we have 4 strands. And C1 is to braid the first two, and C2 is to braid the second and the third. And this is the pictorial representation I'm giving, which is precisely the representation I defined in the previous slide, right? It's just this. Very good. Now, as I said at the very beginning, when you have a braided vector space, you can produce some crazy object, which is known as the Nichols algebra of V. How do we do that? Well, it's a complicated definition somehow, but it's very combinatorial. You don't need anything, but it doesn't show all the structure that you have, right? But of course, even from this definition, you will find, you will recognize why these objects are so hard to study, okay? So essentially what you are going to do is to construct the Nichols algebra as some quotient of the tensor algebra. And how you do this? Well, it will be a graded algebra. In degree 0, you are going to put the base field, K. In degree 1, you will put your braided vector space B. And then, well, in degree 2, you will have V tensor V, maybe with some relations. In degree 3, V tensor V, quotient out by maybe some relations, and so on, right? And these relations are given by the kernel of the quantum symmetrizer, which is what? Well, the map S2 will be identity plus C. The map S3 will be this crazy formula that I wrote there with 6 terms. So maybe you can recognize here what we are doing, right? Essentially, what we are doing is to run over all the elements in the symmetric group S3, but instead of using elementary transpositions of the form I plus 1, I'm just using the braiding in position I plus 1. So you know that every element in the symmetric group can be generated by elementary transpositions, and what I'm just doing is to lift this to the braid group by the representation I constructed before. And then you have an inductive formula for the n plus 1 symmetrizer, which is given by identity tensor, the previous symmetrizer, and then this other expression. Okay, so this is this is the definition, which you immediately recognize that this is going to be very hard to compute, right? Because how do you know when to stop computing kernels of the symmetrizer? It's not clear at all. You don't know if these guys are finitely generated or not. You have finitely presented. You have no clue. Okay. And yeah, but let me give you 2 very well-known examples of a Nichols algebra. So symmetric algebras and exterior algebras are examples of Nichols algebras. So you need to take any vector space, and most of the 2 easiest braidings, the flip map and minus the flip map. And then you get these 2 very well-known examples of Nichols algebras that also suggest some possible applications of Nichols algebras, right? In fact, yeah, so they are quite, they were rediscovered several times. For example, they were considered by Nichols at the beginning, studying Hopf algebras, also by Lustig, studying quantum groups, Andruskiewitsch and Schneider studying again pointed Hopf algebras, Majid doing non-commutative physics, and Voronovic doing quantum differential calculus. And precisely he was using this observation that they are somehow generalizations of symmetric and exterior algebras, right? So you see that they are very geometric objects in some sense. Very good. Now, they have more structure. It's not just an algebra, right? But I will not go into details. So as I said before, they are graded by non-negative integers. This we know. But they are also something called braided Hopf algebras, which I don't care if you don't know what this means, but let me just tell you that they have more structure. They are a Hopf algebra in some category, which is not the category of vector spaces. It's a more complicated category, okay? So you can define Hopf algebras in categories which are a bit, you need a braided tensor category, and there you can define Hopf algebra, and there is a particular braided tensor category that where you can realize this Nichols algebra as a braided Hopf algebra. I will explain this later. Okay, but you have more structure. It's not just an algebra given by some crazy quotient. So I will need this for later. I mean, since it is graded over non-negative integers, of course, you can define the Hilbert series. So putting the dimensions of each homogeneous component as coefficients in some polynomial or in some series, formal power series. And of course, if the Nichols algebra is finite dimensional, then you get a polynomial instead of a series. Okay, this is called the Hilbert series of the Nichols algebra. Now, which is the problem I want to discuss? I would like to classify or to discuss the classification problem of finite dimensional Nichols algebras. So of course you can, I mean, essentially anything that you would like to say about Nichols algebras is interesting and an open problem, right? I could consider, for example, finite Gelf and Kirillov, or ask if these algebras are Noetherian. I mean, whatever, right? But the problem I want to address is the classification of finite dimensional algebras, Nichols algebras. And why? Well, because with this, I can classify certain family of Hopf algebras that includes quantum groups. Okay, let's say this like this. But I'm not interested in all possible Nichols algebras over braided vector spaces, because I have a very concrete goal in mind. And for that goal, it is enough to consider Nichols algebras over groups. So thinking that a Nichols algebra will be some very complicated invariant of groups, and then try to classify those that are finite dimensional. Okay, because in fact, for the applications, they will be these Nichols algebras will always come from braided vector spaces of group type. Okay, good. So, but like just dealing with the braided vector spaces in a complete abstract sense is complicated, because there is no structure or not a lot of structure, right? So a better way of dealing with them is talking about Jeter-Drinfeld modules over groups. So what is a Jeter-Drinfeld module? Well, let's say that G is a group. A Jeter-Drinfeld module V over the group G is a G-graded KG module. So you have a G module which also has a G grading, meaning that you can decompose V as a direct sum of homogeneous components of degree G for G running in the group G. And then you need a compatibility between the G grading and the G module structure, and the compatibility is that I say there, right? Essentially, that if you act with G on the H homogeneous component, then you end up in the homogeneous component of degree G, H, G inverse. Okay. Okay, so Jeter-Drinfeld modules are very old. They were discovered in 1949 by Whitehead. He was doing topology, right? And then, of course, they were rediscovered several years later in connection to quantum groups and the Yang-Baxter equation. But these are not crazy objects. They are known, right, in math. And they are quite nice. So first of all, every time you have a Jetta-Drimford module, you get a braided vector space for free with this formula that I wrote there, okay? So C on V tensor W. So remember that C is a linear map, and since V is G graded, well, it is enough to know what happens when V has degree G, right? And W is arbitrary. And then this is the formula that you get there. And yeah, this category of Jetta-Drimford modules over Kg is in fact a very nice category. It's a braided tensor category. Meaning what? Well, meaning that you can tensor Jetta-Drimford modules to get a new Jetta-Drimford module, and also you have a braiding, as I explained before, okay? Very good. So it's a very nice category. Now, I want to say something about the classification of Nichols algebras over braided vector spaces. Well, there are two families that I'm interested in. Diagonal type, which means those braiding that come from abelian groups, or non-diagonal type, which are those of group type when the group is non-abelian. In the case of diagonal type, this was solved in characteristic 0. In the case of non-diagonal type, well, again, I can consider two cases. My module V can be decomposable, whatever it means, or non-decomposable, okay? And, well, the decomposable case is solved, but not the indecomposable. This is kind of weird, right? Because how is that possible? In general, in math, you go in the other direction, right? You start with knowing the building blocks, the bricks of your theory, and then you know how to extend. But here is different, and I will try to explain why, okay? Good. So let me first say, something about diagonal type, which is not the case I want to discuss, but I think it is important to mention some references and where these guys appear. So remember, the diagonal type means that you have this particular shape of a braiding, and they are very important in algebra, let's say. So for example, complex finite dimensional Nichols algebras of diagonal type were classified, as I mentioned, by Heckenberger. The list, a precise presentation by generators and relations was given by Angiono. Then there are very strong applications to Hopf algebra, in particular the classification of Andruskiewitsch and Schneider, which more or less would give you an axiomatic theory of small quantum groups, right? So it's kind of deep and important. There are also applications to physics. The work of Semikatov, for example, he found some Nichols algebra structure related to screenings, and also in the work of Simon Lettner. And there are also applications to something known as the Etinghoff-Ostrich conjecture, which is about finite generation of cohomology. There are several people working on that, right? Like Andruskiewicz, Angiono, Petsova, Witherspoon, and some others, okay? Very good. But this is not what I want to discuss. I would like to discuss the non-diagonal Nichols algebras, okay? So where do they appear? Well, there are at least two places where these guys are relevant. One is combinatorial Schubert calculus, more like algebraic geometry. And the other one, of course, is algebra, and in particular, pointed Hopf algebras with non-abelian coradical. If you don't know what this means, just imagine there is some sort of quantum group, but yeah, some other type of quantum group, okay? Finite dimensional quantum group. Good. So first of all, I will show you some examples of indecomposable braided vector spaces. So this example is quite old. It's from 95, I think. It appeared in the work of Fomin and Kirillov about Schubert calculus, where they gave a combinatorial model for doing Schubert calculus, and in particular to try to solve this some very old problems in Schubert calculus, and also in the work of Milinski and Schneider related to Hopf algebras. So you take the group will be the symmetric group S3, and you take the conjugacy class of involutions there. So you know that there are three, okay? 1, 2, 1, 3, and 2, 3. So you take a complex vector space, V, with bases A, B, C, where A corresponds to the transposition V1, 2, B to the transposition 1, 3, and C to the transposition 2, 3. And the braiding is essentially conjugation, but with a minus, okay? This is, I mean, it's a braid. Now, this braided vector space, of course, can be realized as a yet a dreamful module over the symmetric group S3, okay? Good. Now, you compute the Nichols algebra. In degree 2, there are 5 relations. A squared has to be 0, B squared has to be 0, C squared has to be 0. And then you have also AB plus BC plus CA is 0, and finally AC plus BA plus CB is 0. So these are the quadratic relations. And then you can prove, by hand even because it's rather small, that your algebra will be finite dimensional, and you can give a basis, which is the one that I wrote there. And you see, of course, you can also write the Hilbert series, right? Which is a polynomial in this case. Fun fact, this guy is symmetric. So you start with, is unimodular. You start with a 1 and you end with a 1 as a coefficient. But also, you know, it's symmetric, right? The first one is the same as the last one. The second one is the same as the second to last, and so on. And this, in fact, this maybe you know this is some sort of Poincaré duality that you have here for these algebras. This is indeed a theorem, right? Something that happens and in every finite dimensional Nichols algebras, algebra, but this is the reason of this is because these guys are a braided Hopf algebra, right? So this doesn't follow only from the algebra structure. You need to use the braided Hopf algebra structure. Also, you need to use the braided Hopf algebra structure to know that this will be more or less all the defining relations, right? But okay. So you have an example of dimension 12. Very nice. It's very old, this example. Yeah. Okay. So I will give you some other family of braided vector spaces, right? So you can generalize this. You can, instead of using -1 as the constant that you were using in the braiding, you can, of course, put some other root of unity, right? And it was an open problem for some time to know whether this algebra is finite dimensional or not. Okay, you know what happens with if omega is 1 or if omega is -1, but then no one knew. And this we recently solved with Heckenberger and Udimeir, and we know that the dimension is infinite. Okay, I will mention this result later. Second example, similar to the previous one. Now let's take 3 cycles, one of the class of 3 cycles in A4. In A4, you have 2 conjugacy classes of 3 cycles. Take one of them, doesn't matter, and yeah, again, you consider a basis on this class and a braiding with a -1. This braided vector space cannot be realized as a yet a dreamful module over A4, but you need to use C2 cross A4. Okay, this is because of the -1, but that's okay. And again, you can compute the defining relations. You have several relations in degree 2, and then you have one crazy relation in degree 6, and this is enough to know that the Nichols algebra will be finite dimensional. It will have dimension 72, and this is going to be the Hilbert series of your algebra. Okay, this is it's pretty old. This example is from, I don't know, it has at least 20 years, probably more. Okay, 25 maybe. Now, yeah, as I said before, right? There is another natural open problem here. What happens if you want to know what are the Nichols algebras over A4 and not with this C2 cross A4? So again, you will have to deal with braidings of this type, right? You have the same conjugacy class as before, and then you multiply by some omega. And yeah, now omega is a primitive cubic root of 1, for example, or a root of other order. And what happens? And we recently solved this in a joint work with Andruskiewitsch and Schneider that I will discuss later, okay? Good. And then I want to mention some other problem. This is still open. and is related to Fomin-Kirillov algebras. So this is from 1995. So you get xn, n is bigger or equal than 3, and xn is the conjugacy class of transpositions in the symmetric group. Again, you take a complex vector space with basis in your conjugacy class, and the braiding is conjugation with a minus. The question is when this algebra is finite dimension, okay? And you know, we saw the example of n equals, where n is equal to 3. This is the first example I discussed. You can also prove that this algebra is finite dimensional for n equals 4 and 5. But for 6, we don't know. This is still open from 1995. And it is also not known whether this algebra is quadratic or not. If there are more relations, or the only relations that you have are, you know, those in the grid 2. And these problems are still open, okay? And this is kind of the open problem that we have in this area. And on the other hand, there are very few examples of finite dimensional Nichols algebras over indecomposable braided vector spaces. I know that I still have to give you the definition of an indecomposable braided vector space, right? Because it's not indecomposable as a module. It's something a bit more complicated, but I will explain this in a bit. So this is the full list of finite dimensional Nichols algebras over indecomposable braided vector space. Here I'm doing this over the complex numbers, right? But okay. Yeah. So you see, here I have the dimension of V. So the dimension of V is 3, 4, 6, 5, 7, or 10. These are the only examples where I know that this happens. The dimension of the Nichols are, well, these numbers that you see there. There are some repetitions, but yeah, these are, you know, they are non-isomorphic algebras, right? They are related by some form of twisting or something, but they are different algebras. And there I also tell you which is the group or a group where you can realize this braided vector space as a Jette-Drimfeld module. And you can see, for example, that in the first cases, so all of them but the last two, the group is always solvable. And the last two, of course, is over S5, which is not solvable. This will also play a role later, okay? Very good. So in general, I have symmetric group S3, symmetric group S4, SL23, A4 cross C2, or some semi-direct products, okay? So the question is, well, it seems so hard to find Nichols algebras that it might be the case that this list is the full list of Nichols algebras, okay? Which essentially will tell you that, you know, if you want to find this sort of finite, say, general quantum groups, you have classical quantum groups, then you have some other things, and then a couple of more very exceptional non-commutative things, and that's it, right? Good. So let me explain what this means, what indecomposable means, and what happens with the solution in the decomposable case, okay? So it all starts with a very old remark by Matthias Grania that says that if the square of the braiding is the identity, then when you do the Nichols algebra of V plus W, well, is nothing but V as a vector space is the Nichols algebra of B tensor the Nichols algebra of W, okay? So if you want to classify finite dimensional ones, well, I mean, nothing new will happen here, right? So this means that it's not a good idea to consider this B plus W as a decomposable thing, but because in the end, solving this is just follows immediately from knowing what happens with the Nichols of V and the Nichols of W, right? So that is why decomposable for us will require the assumption that the square of the braiding between V and W is going to be different from the identity, okay? So, and then I need a technical definition, which is the support of a Jette-Drimfeld module. So remember that a Jette-Drimfeld module of a group is this direct sum of G homogeneous components. And well, the support is the set of G where V of G is different from 0. And this is always a union of conjugacy classes of G, okay? Because of the definition of a Jette-Drimfeld module. Now, the theorem we proved with Heckenberger around 10 years ago is the following. Well, it gives a full classification of Nichols finite-dimensional Nichols algebras in the case of sum of two modules where this sum is decomposable, right? So the assumptions are the following. G has to be non-abelian, because if it is abelian, it's something that it was already solved. V and W are two absolutely reducible yet dreamful modules over the group algebra. What does it mean absolutely simple, irreducible? Well, I mean, K is an arbitrary field. This means that they are irreducible after field extensions, okay? If your K is the complex numbers, then it just means irreducible, okay? And then we are gonna assume that G is generated by the support of B plus W, which means that, you know, G is what you need and nothing more to realize your V plus W, and that the square of the upbraiding is not the identity. Otherwise, you are in the composable case, right? And then, if your Nichols algebra is finite dimensional, then you can describe very precisely which is your group. So essentially, your group will be a quotient of a very small dihedral group or SL23. Okay. So it's yeah. Yeah, to be more precise, will be either a quotient of a certain central extension of SL23, sorry, or of a central extension, or a quotient of a central extension of a very small dihedral group. Okay, so I have a very, very precise description of the group that you know is realized in this setting, and then from this I can obtain essentially all the information I want. I can describe very precisely the structure of V and the structure of W and the dimension of the Nichols algebra. So, for example, I put here complex numbers just to simplify the consequences, but of course this holds for arbitrary fields. So this is the theorem in the case of the complex numbers. So the assumptions are the same as before. Then you know the group, and then you just perform the calculations to know which algebras you will get. And well, V plus W can have dimension 4, 5, or 6. And these are the possible dimensions of the Nichols algebras. And that's it. So this gives you a full classification of Nichols algebras over the composable rank 2 yet dreamful modules over the complex numbers. If you remove complex numbers, you have more finite dimensional Nichols algebras that can appear, right? So I mean, this is a bit technical as a slide, but let me give you an example of how the group looks. For example, the group T, which was a central extension of SL23, will look like this, right? You will have 5 generators. Z is a central guy, and then X1, X2, X3, X4 more or less will be a lifting of the conjugacy class of unipotent elements in SL23, right? So these are elements satisfying these relations that you see there. Yeah, and how do the module V look like in this case? Well, I mean, it's one-dimensional module with basis V, and then this is how the elements of my group will act. So Z will act by some scalar given by a representation or a character, and Xi will act by some other character. And yeah, this is like the table of the module, right? So for example, X1 acting on the first basis vector W1 is going to be minus W1. X1 acting on W2 will be minus W4, where W4 is what? Is this element that I have there of degree X4, minus X3 W1, and so on, right? So it's a very, very precise description of the module W and the module V, okay? So I don't need to go over all these details. You have, of course, some conditions that need to be satisfied for the representations creating these modules, but it's very, very precise, right? You cannot say more. Yeah, and in this case, well, you need to assume some, as I said, some conditions, which are those that I wrote there, and then you will get a Nichols algebra of dimension, this number that I have there. It's a very, very big number, Nichols algebra, okay? Good. But as I said, right, the theorem is also true for arbitrary characteristics. And if you allow all possible characteristics, you have more examples. And this is the full list. Okay? Good. So this solves the problem of classifying Nichols algebras over groups when you have two indecomposable summands. What if you have more than two? If you have 3, 4, 7, 24 indecomposable summands? Well, you need again the definition of decomposable. And the definition is not very complicated, right? So you need to ask that your tuple, now which contains theta direct summands, admits no decomposition in two guys, m prime plus m2 prime, where with non-zero, of course, where the square of the braiding is the identity there. So this is not allowed. That is a natural extension of the definition of decomposability in when you have two summands. Okay. And yeah, and then you need, I mean, in principle, you will get a classification, but yeah, I mean, you have a arbitrary number of summands, so it's not as you did before, that you can describe the groups. I mean, you can, but it's very annoying, right? To describe the groups or describe the modules is a crazy thing. So you need a better way to encode this information. What is what you do? Well, you are gonna put this inside a diagram, a graph, okay? And essentially, amazingly, what you will get is that those Nichols algebras that will have will be finite dimensional is because the tuple will be attached to a thinking diagram of finite type with some extra decoration. So these thinking diagrams with decorations are called skeletons. And yeah, you have a dictionary that says, well, a tuple with this and that properties goes to a diagram with this of that properties. And then, yeah, you will get thinking diagrams with a little bit extra of information. So for example, these are the diagrams you will get in type ADE, which are more or less the same as you know, with the only difference I see is that in every vertex you have 2 points, right? This means that, so every vertex corresponds to a module mi, and these 2 points are telling you that the dimension of mi is going to be 2, okay? Just this. And then, of course, you can have some more crazy things outside type ADE, which, as you expect, are a bit more complicated, right? Like, for example, well, some crazy guys will appear in characteristic 3 or characteristic different from 2. And yeah, you have here like a particular distribution or configuration of vertices that tells you something about the structure of this particular module, which is precisely the structure given by conjugation of transpositions in S3, but that's a matter. As I said, you have a dictionary, right? So this is not a problem. The important thing is the theorem. Again, we proved this with Heckenberger, and the theorem says that if you have a tuple of at least 3 absolutely reducible summands, well, you will have a finite dimensional Nichols algebra if and only if, well, you can attach to this M a thinking diagram of finite type. So these Nichols algebras are classified by thinking diagrams. These are a thinking type classification, right? Which I find super, super nice. Good. So again, as before, I mean, I could describe the groups, right? But this is too complicated and is irrelevant at this point. But what is more important is to describe the Nichols algebras, and I can do that, right? The modules are, of course, described in the diagrams, and the Nichols algebras and their dimensions are also described. So here are the dimensions you get in type ADE. Okay, so for example, in type E8, you get 4 to the 120, and so on. Okay, so it's yeah, I mean, you cannot say more, right? This is solving the problem completely for decomposable tuples. And funny enough, this will have very, very strong applications to the indecomposable case. Okay, so the idea of the applications will be this. So there is some sort of functoriality property of these Nichols algebras, in the sense that if you have a subspace of V is a braided vector space, and you have a subspace which is stable under the braiding, which is called a braided subspace, then you have an inclusion of the Nichols algebras. And then, well, if the Nichols algebra of W is infinite dimensional, then so is the Nichols algebra of P. And this very simple idea can be used to in connection with the theorems I mentioned to understand more what is happening in the composable case. Let me give you some examples. So long time ago, we proved with Andruskiewicz, Fantino, and Grania that if you take a Nichols algebra, if you take a non-zero yet dreamful module, complex yet dreamful module over a alternating simple group, then the Nichols algebra will be infinite dimension. And this is proved using more or less the idea that I told you before. And a similar result holds for sporadic simple groups. There are three exceptions, which are Fisher 22, the baby monster, and the monster. There we don't know, okay? But more or less the same theorem holds for 23 of the 26 sporadic simple groups. Again, this was proved by in collaboration with Andruskiewicz, Fantino, and Grania. We don't know, as I said, we don't know what happens with Fisher 22, baby monster, or the monster. This is still an open problem. I think now probably we can say something about this, but yeah, still not written down. Yeah, and there are also several results concerning Nichols algebras over groups of finite simple groups of Lie type. And a lot of work has been done on this by Andruskiewicz, Carnovale, Constantini, and Gaston Garcia. So all of this points to the following conjecture, right? There are no finite dimensional Nichols algebras over finite simple groups. Non-abelian simple group. I forgot non-abelian there, right? Because, yeah, for abelian is different, right? But yeah, this is still open, but quite, we are quite close. This is nice. And just let me tell you a bit about the complement of what happens in the composable case for simple groups. So with Heckenberger and Meir last year, we proved the following result. The technique used here is completely different. We were using some deformation theory, and the classifications result I told you in prime characteristic to get results in characteristic 0. So you have a non-abelian group G, and then you have an irreducible complex yet a dreamful module of prime dimension. Again, you need to assume that the support of B generates G, which is a reasonable assumption, right? Otherwise, why you have G if it is not related to your yet a dreamful module B? Then the Nichols algebra will be finite dimensional if and only if is one of the algebras that you knew from before that were finite dimensional with prime dimension of the braided vector space. So essentially it's one of the 5 algebras I wrote there. The dimension of V can be 3, 5, or 7, and the dimension of the Nichols will be one of them. That's it. All the other examples will give infinite dimensional Nichols algebras. In particular, for example, if you change the problem that I was telling you about taking the dimension of B equals to 3 and then a cubic root of 1, this will be infinite dimensional because it doesn't appear in this list. And we used some of the techniques here in combination with other techniques to obtain a more general result. With Andruskiewicz and Andruskiewicz and Heckenberger, we proved last year the following result. So suppose that G is solvable and non-cyclic, and V is a complex yet a dreamful module. Again, you assume that the support of the module generates G. If the Nichols algebra is finite dimensional, then your V is irreducible, and your Nichols algebra is one of those that you know from before. Essentially, you remember the list of Nichols algebras I gave you? There were all but 2 oversolvable groups. Well, oversolvable groups, the list is that one. There are no other finite dimensional Nichols algebra oversolvable groups. We don't know what happens in the non-solvable case. What we guess is that over finite simple non-abelian groups, there will be no other finite dimensional Nichols algebra, but then we don't know, right? What can happen when you do extensions? This still is we don't know. But this solves the problem for solvable groups, which is a lot of progress. Okay, and yeah, I mean, this also has application in Hopf algebras in some sense. You probably know Fay-Thompson theorem in finite group theory, which says that groups of odd order are solvable. Well, as an application of that theorem, you can get some sort of Fay-Thompson theorem for finite dimensional pointed Hopf algebras. So yeah, so if you have a finite dimensional pointed Hopf algebra of odd dimension, then you know it will be, very well what it can be. Okay. I don't want to give you the precise the statement of the theorem because it's rather technical and it's irrelevant at this point. But yeah. So yeah, I think this is everything. Thank you very much.
Thank you very much, Leandro, for very nice talk. It's an impressive result. Yes.
Thank you.
Is there some question? Okay, I just want to ask you more about you say about application. So at the end of your talk, you say about the application to Hopf algebra.
Mm-hmm.
But I'm not sure that means that the classification of Nichols algebra gives some more structure of the Hopf algebra. Or
Yes, there is something called or known as the lifting method, which essentially gives you some sort of program to classify say pointed Hopf algebras, but of course it's a bit more general. But so the idea is like this: you want to classify finite dimensional pointed Hopf algebras over a given group, right? So you fix the group. You compute all finite dimensional Nichols algebras over this group. Okay. Then what you are gonna do is produce semi-direct products, say, of this Nichols algebra with the group algebra. And then the idea is that all pointed Hopf algebras that you wanted to classify will be deformations of this sort of semi-direct product. Okay, this is the method. And well, a very, very hard step there is to classify the finite dimensional Nichols algebras. Then you have to compute all the deformations, or I mean, but this part is crucial, right? Because it's very, very hard. Yeah, this is the idea. And also you not necessarily want to classify, right? But what happens in practice is that most of the things that you would like to say about these Hopf algebras, well, in general, will be just something that you can see at the level of the Nichols algebra. That is why that step is so important and so hard, right? Yeah.
yes. Is there some more questions? So I just asked if you try the recent time some how to say assistant from the AI to classify this algebra or no?
No, not at all. No.
They are not good enough.
No, this is it's so one uses a bit of Lie theory because there is the composable theorems used an invariant given by not a Weil group but a Weil groupoid. So one uses this, and then a lot of group theory. It's really a lot of finite group theory.
Yeah.
And for the thing of the sporadic simple groups, we were using, of course, computer algebra, right? Because this is the way of dealing with sporadic groups. But yeah.
Yeah, so that is why I think about the more powerful machine learning method.
Yeah, but not AI, not at the moment, right? Maybe
not
in
at the
some
moment,
years you can reproduce some things with AI, but at the moment AI seems to be not good enough for this.
Yeah. Okay, let us thank the speaker again.